Well, hello everybody, and welcome to lecture number 2 of this series. And the first thing I'd like to do is to take back one stupid thing that I said in the first one, which was that the world was mostly made of carbon, nitrogen, oxygen, and sulfur with hydrogen. In fact, the world, in particular the world that we walk on, is made of largely of silicon and aluminum oxides. I had simply forgotten about rocks because I was talking about perfumes, but it's inexact to describe the world as I did, so I take it back. And the second thing is, I'm going to have in this series one perfume every day to keep me in a kind of creative state. And this one is one of my favorites, and you can see I've used it a lot. I even lost the cap. The bottle's half empty, and it's called Miyako by a small company called Euphorie. And it's a company that's run by two self-taught Chinese perfumers in Kuala Lumpur. And it's one of the most beautiful perfumes I have ever smelled. When I smelled this, I just, well, basically, I had not written anything about perfume for many years. And when I smelled it, which was, I don't know, what, 4 or 5 years ago, I decided to go back to writing about perfumes. Anyway, so today things are going to get a little bit more difficult because I want to explain to you the very important question of what keeps liquids and molecules together. What makes a molecule stick to each other. And of course, this is an important question because what makes them stick to each other will also make them stick to the receptors inside your nose, which we're going to talk about in later lectures. Now, it's very important to remember a few basic things. First of all, smell molecules do not have electric charge. If they had electric charge, they would probably not evaporate. Like, for example, kitchen salt, sodium chloride. The sodium has a positive charge, the chloride a negative charge. And if you pour salt on the table, it's going to be there for all eternity because the forces required to separate an electric positive charge from a negative one are enormous compared to the energy that's available, which is the energy of thermal motion. So what forces keep molecules together? Well, there's what's called a chemical bond between two atoms. So those are electrons that are in common to both atoms, and that's quite hard to break. That's the stuff of chemistry. For that you need temperatures of typically 160, 200 centigrade, that kind of thing at least. And so there's not going to be any bonds, chemical bonds made by odorants in the nose. And if there were, if an odorant had a chemical bond to whatever it was sitting on, it would not come off and become a smell. It would be stuck there. So we're dealing here with weaker bonds. And there are two types of very weak bonds between, relatively speaking, between molecules that we're going to deal with. One is the hydrogen bond, and the other one is what's called dispersion bond or vander Waals forces. It has various names. Mostly van der Waals, named after a Dutch physicist who was the first to study them. Now, it may seem surprising, but neither the hydrogen bond nor van der Waals bond are all that well understood at a fundamental level. They are hard to understand in quantum mechanics. They're hard to calculate with the appropriate mathematical equations and software. And so it's interesting that the hydrogen bond and the van der Waals forces are everywhere. but at the same time, not 100% understood. In fact, there's many different ways of explaining both of them that I've heard from physicists and physical chemists, and sometimes they seem almost incompatible with each other. But I just want to represent to you that they are extremely important, because what the forces that hold the molecule of DNA together, you are all, I assume, familiar with the double helix of DNA with the two strands of DNA going around each other. Well, in this direction, the stack direction, the bases of DNA are held together by van der Waals forces. And in that direction, the direction that is involved in replication of DNA, they're held together by hydrogen bonds. So you can see that those two forces, hydrogen bonds and van der Waals interactions or forces, are absolutely crucial to living things. And they are actually the two types of interactions that are fundamental to odorants, to the behavior of odorant molecules in solution and on a surface, and also to their recognition by the nose. So the first thing I'd like to show you is what's called a molecular dynamics simulation of molecules. So how is this done? I have a piece of software on my computer, which is, by the way, an extraordinarily good piece of software, and parts of it are free. You can download them and play with it yourself even on a fairly small laptop. It doesn't have to be a very powerful computer, and it will teach you an awful lot of chemistry to play with that. And it's a software called Yasara, which means yet another scientific artificial reality application, which I love. And it was designed by, I believe, a Swiss physical chemist and computer buff, Elmar Krieger, his name is. And it is absolutely wonderful to see molecules in action. And the first thing I want to show you is an illustration of hydrogen bonds. So the first thing that's important to remember is that water is a totally strange liquid. Among the solvents that you can use in chemistry, you can use a whole variety of solvents. You can use methanol, you can use chloroform, you can use acetonitrile, you can use all sorts of different solvents. But water is very peculiar because it's a very small molecule, and then it has, despite being a small molecule, it has a very high boiling point, 100 centigrade. So why, so for example, the boiling point of pure alcohol, which is a heavier molecule, would be much lower. That's how you can distill spirits from wine. You take wine, or rice wine for that matter, and you heat it up, and the first molecules that fly out and can be distilled are alcohol molecules. You can make strong spirits this way. The water stays behind. The water stays behind because the water molecules are stuck to each other. What makes them stick? Well, from what I've said so far, you'd probably guess it was hydrogen bonds, and you'd be right. So if you look at a molecular dynamics simulation, so what I've done in this simulation is I've made a small box. I have filled it with water molecules. Then I have chosen a particular set of parameters that describe the interactions of the molecules with each other. And these parameters are worked out by physical chemists, and the way they are worked out is that they choose numbers that describe the forces at different angles and different distances, and the numbers have to fit experimental values. These aren't numbers that are just simply invented. They're numbers that are so-called benchmarked against the real thing. So if you look at the molecular dynamic simulation, the water molecules are at 300 Kelvin, which is room temperature by convention. And when you turn on the simulation, the molecules start jiggling, and the yellow stripy things between them are the hydrogen bonds that are forming and breaking. And you can see that even though some molecules might escape once in a while, the hydrogen bonds are pretty much gluing the thing together. And that is because the force of a hydrogen bond, the strength of a hydrogen bond is, meaning the energy required to break it, is roughly twice or three times the energy that things have at room temperature. So it's going to break some of the time, but mostly it's going to stretch and then come back together. And that's the situation for water. Now let's compare that to another molecule that's, in fact, if anything, heavier than water, but does not make hydrogen bonds, and that's hydrogen sulfide. And if you look at the molecular dynamic simulation of hydrogen sulfide, same temperature, same method, I make a little box, I fill it with hydrogen sulfide, then I run the simulation, you see that they're not attached to each other, and they tend to fly off in all directions. This is very important because this tells you something about the ability of a droplet of any compound to evaporate. So even though water does evaporate and things dry eventually, it does so rather more slowly than you would expect from its size and molecular weight. So the third one that I want to show you is ethanol, which is the molecule in which most perfumes are dissolved. In fact, fine fragrance is called alcoholic perfumery because the perfumes are dissolved in ethanol. And that is part of the reason why in many Muslim countries where ethanol is not, alcohol is not allowed, they tend to use oil-based perfumes, attars that are, they used to be dissolved in sandalwood oil, but now they use other solvents. But ethanol is somewhere between, if you want, water and hydrogen sulfide, because it makes fewer hydrogen bonds. In fact, it makes 2 instead of 3, and so it's slightly heavier, but it does fly off. Now, the other force that I mentioned, the van der Waals force, is a very strange force that occurs between electron clouds. When you have a molecule like benzene, which is made of 6 carbons and has 2 clouds of electrons, one on each side, going around the molecule, those clouds are sticking out from the plane of the molecule. And when you bring 2 of the benzene molecules together, what happens is those clouds influence each other in such a way that when one of them spontaneously fluctuates because of quantum mechanical fluctuations, the other one adjusts to that. And the net result of these mutual influences is a weak attractive force. Now, when I say weak, it's again, it's very weak compared to the 2-electron bond that we talked about. It's also a little bit weaker than the hydrogen bond, but it's still strong enough to, for example, make things stick to each other, like, for example, to make molecules stick to each other in a perfume. So that if you put perfume on the skin, and there are a lot of these van der Waals interactions between the different components of the perfume or between the perfume itself and your skin, and that's also possible. There are plenty of that sort of electron clouds in the molecules that make up the skin. Then you will get fairly, strong interactions. I mean, van der Waals are not strong, but strong enough to delay the evaporation of the molecule for a remarkable amount of time. And in fact, this is used, there are many compounds in perfumery that are known as fixatives, and they serve 2 simultaneous purposes, usually. One is to basically make the other molecules stick to it. So you have a fixative in a fragrance, and what happens is the small molecules tend to stick to the fixative, and their evaporation is delayed, so the fragrance lasts longer, which is a very desirable thing. And the other thing is the fixative can have its own smell. So typically musks, for example, are both. They are fixatives in the sense that they delay the evaporation of the fragrance itself, and then of the rest of the fragrance, and then they also have their own smell. There are other fixatives like phytol, which is a 20 carbon alcohol, which is a perfectly good fixative and has no smell of its own. It just sticks to the rest of the fragrance and keeps it in. So just to illustrate that particular property, I've just made a molecular dynamics simulation of the classic, if you want, molecule that demonstrates van der Waals interactions, which is benzene. Benzene is interesting because it was the first molecule in which these clouds of electrons were predicted to occur, in fact detected, and also because it's a fine instance of what is called an aromatic molecule, and not in the sense that we understand, the perfume chemists understand aromatic, but in a completely different sense, which is it means that the electrons are not particularly localized over a given bond, but they move around the entire molecule. In the early days of chemistry, it was thought that the property of having a smell was linked to this movement of electrons. This turned out not to be the case. There are plenty of odorants that do not have these electron clouds, but the name stuck, and so they're called aromatic molecules. And in fact, there's a property called aromaticity, which is the property of having these clouds. So the molecular dynamics simulation of benzene shows that indeed the molecules are weakly attracted to each other, but that, of course, they fly off. When you fill your car with petrol, much of the smell that you get is due to benzene, which is not a good thing because you should not breathe benzene. Benzene is a strange molecule in terms of toxicity because it gives very, very long-term toxicity. You can breathe benzene intensely on one day, and 20 years later you end up with bone marrow cancer. So you have to stay away from benzene if you possibly can. So to summarize what we've been up to in this lecture, I've tried to give you a feel for the different kinds of forces that hold atoms together and hold molecules together, because those forces will govern both the performance of a fragrance as when it's put on a warm surface like skin or on a cold, relatively cold surface like fabric, because the molecules will be sticking to each other, to the fabric, to the skin, and evaporating at different rates, and that will control the overall shape of the fragrance. And what I want to finish off with is the extraordinarily small scale of all these things that I'm talking about. It's easy to, when you look on a computer, to imagine that somehow these little balls, first of all, that they have colors, that the elements are naturally colored. They're absolutely, of course, not. The colors are purely conventional. And also, they feel sort of solid and nice and shiny. In fact, all of them are electron clouds. And the surfaces of molecules, the electron cloud surface is rather less sharp than what is shown in these spherical models. It's a soft surface. And they're extraordinarily small. I mean, when I showed the molecular dynamics simulations, the size of the initial chunk of molecules before they start flying off is 2 nanometers from one end to the other. 2 nanometers is 2 millionths of a millimeter. 2 millionths of a millimeter. So if a hair is, I don't know, 10 microns, that's going to be 10,000 times smaller than a hair, which is hard to imagine, but also which makes you understand why proving that atoms exist was such a hard undertaking in chemistry. In fact, it was only in roughly 1904 that the existence of atoms, which had been imagined or predicted by nearly 3,000 years ago was in fact correct.